Good morning, everyone, and welcome to the JKMRC Friday Seminar Series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we would like to acknowledge the traditional owners and custodians of the land on which we meet today. We pay our respect to their ancestors and their descendants who continue cultural and spiritual connection with country. And we recognize their valuable contributions to Australia and the global society. It's my great pleasure to welcome Evelyn Mervine. Dr. Evelyn Mervine is a geoscientist and carbon management expert. She has extensive experience working in the mining industry in Australia, North America, South America, and Africa. She currently works as a Carbon Mitigation Principal at Anglo American and is also an Adjunct Fellow in the School of Environment at the University of Queensland. She has an Earth Sciences degree from Dartmouth College and an MSc degree in Carbon Management from the University of Edinburgh, and a PhD degree in Marine Geology that was jointly awarded by MIT and Woods Hole's Oceanographic Institution, Today, her talk will be about unreported carbon emissions from deforestation at mine sites. Please join me in welcoming Evelyn. Thank you.
Thank you so much for the invitation to present today, Belson, and for that wonderful introduction. The first thing I would like to say is that I do work for Anglo full-time, but today I'm wearing my University of Queensland hat, so nothing that I say today represents my industry role. I'm going to be talking about research that I started a few years ago when I was doing my master's degree in carbon management, and which I've continued over the past couple of years here at the University of Queensland. I'm going to be focusing on deforestation at mine sites and discussing the topic of carbon emissions from this deforestation, which currently are largely not included in mining company greenhouse gas emissions reporting. Moment, do I need to click here? I'll just take the title off of my cover slide. This is an image which is an example of this deforestation. This is an image that I took earlier this week of Soroweko nickel mine, which is in Indonesia. And you can see here the contrast between the dense tropical forest and then the land that has been cleared from mining. If you zoom out, you can see the scale of what deforestation has occurred at this particular mine site since 1977. And later in the talk, we'll return to nickel mines as an example and talk a little bit about some of the emissions that are happening in Indonesia from this mining. Today, I will be focusing on nickel. I will make some broad comments about the relevance of carbon emissions from deforestation at a variety of commodities. The reason I'm going to focus on nickel is I recently published a paper with my co-authors who are listed on this slide, including a number of researchers here, Rick Valenta, and at the University of Queensland. And we did our best to quantify the significance of the emissions from deforestation at mine sites globally, nickel mine sites. We published our research in January in Nature Communications. It's open access, so anybody who would like to read it can go online and download the paper for free. I'm going to be covering quite a bit of ground during this talk. Just a moment, I can see myself on this screen and not my slides. Minimize that. I'm going to start by talking about why this matters, and not why this matters, but why potentially you, the audience here, and I've tried to judge who my audience is, why this should matter to you. I'll then present our broad research questions, which I'll return to at the end of the talk, and we'll see how far we manage to get in terms of answering those research questions. And I'm going to present some background. I'm going to take quite a bit of time to go through this background because I think there's some confusion in the mining industry and even among carbon professionals about some of the terminology and some of the classifications of emissions into the different scopes. So many of you may have seen these terms before, you may already have a good familiarity with them, but I think it's important for us to look at the definitions very carefully and make sure that we're all on the same page before I go into my case study about nickel mine sites and then go on to some broader comments. In terms of where the carbon is coming from, there's a nice picture here that I took in Brazil a couple months ago of a very old tree. That tree is likely hundreds of years old. And when you cut down trees like that, there's a lot of carbon that's stored in those trees, and that carbon generally ends up in the atmosphere. So that's another visual image of what we're going to be thinking about today. I'm starting this talk a little differently than I normally start science talks. Normally, I jump right into the numbers and the facts and the science, and I've stopped doing that recently. And the reason for that is that I read an excellent book by the climate scientist, Dr. Katherine Hayhoe. And she talks about many wonderful things in this book. I really recommend that you read this. But one of the things that she points out that really resonated with me, and I've experienced this many times, is that often talking about climate change science facts is not effective. It doesn't motivate people to go and make changes. The message doesn't land with people. It's really important before you get into the science that you try and connect with people. You find a common interest where you can really say, here's the facts, and this is why this really matters to you. This is why this is going to impact your life. This is why you should care about this. So I'm going to start with that today. And if you haven't seen Dr. Hayhoe's excellent TED Talk on climate communication, watch it this weekend. It's excellent. So why does this matter? For those of you who live in southern Queensland and northern New South Wales, you would have just experienced Cyclone Alfred. It could have been worse, but I believe that operations here at the university were disrupted. Many of you probably lost electricity, had some flooding, so on and so forth. So climate change is not something that's affecting us in the future. It's something that's affecting us now. And we haven't had a cyclone in this area for 50 years. The warming of sea surface temperatures will likely mean that we see more and more of these cyclones in the coming decades. The other reason why what I'm going to talk about today matters is many people in this audience would be very aware of the big impact that increases in nickel mining in Indonesia have had on the Australian nickel industry. Essentially, most of the mines have now shut down, and many, many people have lost their jobs. Maybe some of the people in this audience or who are listening online have been affected by that as well. Because carbon emissions from deforestation are generally not reported, perhaps the mines here in Australia, which are in desert areas which don't actually lead to much deforestation, are not really on a level playing field with nickel mines that are located in dense forest regions. And maybe this reporting could help level that playing field and make Australia more competitive in that sense. Now that hopefully you have in your mind a couple of reasons why you should pay attention, let's get into the science. I have three overarching research questions that I started with about 4 or 5 years ago when I first started thinking about this topic during my master's research. The first question is, there must be carbon emissions from deforestation at mine sites, but are they significant? Are they something that we even need to report? Or compared to the emissions that you have from electricity, from production, from the vehicles, are they insignificant? So I wanted to answer that question to know if it's something that you even need to worry about reporting. Assuming that they are significant, how variable are they? Can mines distinguish themselves by having a lower carbon footprint because they have less deforestation? Could that be a way to encourage them to have less deforestation? And finally, where do you get this information? Who is responsible for actually tracking these emissions? We'll come back to those research questions at the end of the talk. I want to take the next 2 slides to explain 2 terms that I'll be referring to during this talk that are important to understand. The first term is biomass carbon. And you might have noticed the paper title that I had, it didn't say deforestation. I was talking about biomass carbon losses. Biomass carbon is actually a fairly simple concept. It's the carbon that is stored in organic matter. So what we're looking at here is the carbon that is stored in trees, in their trunks, in their branches, in their leaves, and also importantly, the carbon that gets stored underground in the root systems. It doesn't just have to be trees. I use the word deforestation, but actually you could think about land use change. So any vegetation that you have, if it's a shrub or a grass, that contains carbon. And you need to think about the loss of that carbon as well when you have land use change that disturbs that vegetation and removes the vegetation. Today, when I talk about the carbon numbers, I'm focusing on the living carbon biomass. So I'm not going to be accounting for leaf litter, for soil carbon. So when you see the numbers later in this talk for nickel mines, bear in mind that there are probably additional carbon losses that we didn't account for because we just focused on the living matter. Living biomass is not evenly distributed in the world. That makes sense when you think about the biomes. There's very different amounts of living biomass carbon stored in a desert versus in a dense rainforest or in a swamp or in all the different biomes that we have on Earth. The best map that I have found to date is this excellent study. It's cut off on the bottom there, but by Spawn et al. And you can see that you've got on the top the above ground biomass carbon, and you have a scale going from 0 to greater than 120. And it's megagrams of carbon, but that's the same as tons of carbon. So you can think about tons of carbon per hectare. That might be an easier unit for you. And on the bottom, you see the below ground biomass carbon, but note the scale there only goes to up to 30. So you generally get more biomass stored above ground, but that does depend on the region. And you can see that particularly in the tropics, you have a lot of biomass storage. You have really, really high numbers. And in other parts of the world, not so much. The other term that's important to understand is irrecoverable carbon. So irrecoverable carbon, the term gets defined in slightly different ways and on slightly different timescales. But this essentially refers to carbon that's stored in a biome that once you have land use change in that biome, once you disturb that biome, you cannot recover that carbon by restoring the ecosystem on any kind of reasonable time frame. So as an example, a tropical rainforest has a very high carbon density. It stores more than 200 tons of carbon per hectare. If you cut that rainforest down and you replant it in 50 years, you will not recover that same density of carbon. And so you talk about this concept of irrecoverable carbon. You cannot always restore carbon back. So there was a really good paper that was published a couple of years ago in 2022 by Noon et al. That mapped out the distribution of irrecoverable carbon, which we need to think about in addition to carbon biomass densities, and identified some particular biomes that contain a lot of irrecoverable carbon. So things like tropical forests, boreal forests, peatlands. And the good thing and the bad thing, depending on where you are, is that you could focus on a relatively small percentage of the world to protect this irrecoverable carbon. So 50% of the world's irrecoverable carbon is located in just 3.3% of land area, and 75% is located in just 7.5% of land area. So in an ideal world, you would have no land disturbance in those areas that have a lot of irrecoverable carbon. Let's talk now a little bit about scope 1, 2, and 3 emissions. And I'm sure pretty much everybody in this room and online has heard these terms and has some idea of what scopes of emissions are. But let's go through it again. And there's many different diagrams that you can take from the internet, from different publications to look at this. The source that I always like to go to when I'm thinking about carbon accounting is the Greenhouse Gas Protocol. And the reason for this is it's kind of like the JORC code for mineral reporting for carbon emissions. This is the most commonly used corporate standard for reporting greenhouse gas emissions, and it's used by many mining companies. So if you want to be clear on the definitions and your reporting responsibilities, it's good to look at the Greenhouse Gas Protocol documents. So in their main corporate standard, which a lot of companies follow, this is the diagram they have for different scopes of emissions. So scope 1 emissions, those are the emissions on your operational site. And most commonly, you think about fuel combustion and the vehicles from emissions. Scope 2 emissions, those are emissions from purchased energy, for example, purchased electricity. Scope 3 emissions are your upstream and your downstream emissions. So to give a couple of examples, it would be the emissions that are embodied in, say, a metal that you buy to build a processing plant. It can include your travel emissions for business travel. And then it can also include the emissions in the products that you sell. So for example, if you mine coal, the emissions from burning that coal in a power plant would be your scope 3 emissions. What you notice on this figure is that there are no deforestation land use change emissions. So where do those fall? They're actually not mentioned in the Greenhouse Gas Corporate Standard. Companies are a little bit confused about how to report them, if they report them at all. Many companies report them under scope 3. And they say, okay, land use change is scope 3. The problem with that is that in order for something to be scope 3, it has to be somebody else's scope 1. So whose scope 1 is it? it's your scope 1. So actually land use change emissions from land that you own or operate should fall under your scope 1. And in fact, the Greenhouse Gas Protocol has recognized that. So in the corporate standard, these items here, which we've seen in the previous diagram, are what are called out in scope 1 emissions, but recognizing that there's a gap. And this is not something that's going to be relevant for all industries, for all companies. If you're a consulting company and you just have some offices, your land use emissions are not going to be material. You really don't need to report them, your land use change emissions. But if you're a mining company, if you are a forestry company, if you're an agricultural company where you have a lot of land, you have land use change, you absolutely are going to need to report these emissions. And so the Greenhouse Gas Protocol has actually recognized this, and they've drafted a supplementary document to the corporate standard called the Land Sector Removals and Guidance. The pilot's actually been available for a while. It's been available since 2022. And Greenhouse Gas Protocol has announced the final guidance will be published Q4 of this year. So there's a lot in that document. I really recommend that if you're interested in this, that you go and you have a read of the documents that are associated with this part of the standard. I want to just point out a couple of things that will be relevant for mining companies here. The first is that from Q4 2025, when this is in its final form, in order to remain compliant with the corporate standard Greenhouse Gas Protocol reporting, you will need to follow this. And if you're a mining company, you will need to report as part of scope 1 your land use change emissions. That's a big change. And I suspect that many mining companies are not ready for that. Perhaps they don't have the data available for that, and they're going to need to think about that very quickly. And there's a lot of specific instructions about how you do this. I'll get into that a bit more at the end with the recommendations, but it's very important to know that this exists. So what I'm talking about today is largely unreported, but into the future, I think there'll be increasing demand that this is reported following Greenhouse Gas Protocol. So what are carbon emissions from mining? How significant are they in terms of the global story? This is the last background slide that I want to go through before I get into nickel mining. So it's hard to get good data, mostly because we don't have good information on the level of carbon emissions from coal mining, from fugitive methane. That's something that isn't quantified particularly well. If you look globally, I took some numbers from McKinsey that were a couple of years old. The mining industry is responsible for about 4 to 7% of scope 1 and 2 emissions, not counting land use change emissions. This is just those traditional buckets that we would have seen in that first slide from Greenhouse Gas Protocol. And the emissions from operations and electricity use are about 1%, which I think isn't too bad considering the huge number of mines, the importance of producing this metal. Coal mining contributes quite a lot of the emissions. So 3 to 6% of emissions from mining are from fugitive emissions from coal mining. That's a problem. If you look at scope 3 emissions, about 28% of global emissions are from mining. But of course, a lot of that is dominated by coal production and the use of that coal for energy. What we don't know is how much, including land use change emissions, adding that onto scope 1 is going to increase emissions from mining. We don't have a good quantification of that. The best that I can say today is that there's been some studies by the World Bank and others that have shown that at least 10% of forest areas are directly impacted by mining. And actually, if you look at the forest smart mining that had those reports that have been produced recently by the World Bank, up to a third of forest areas are indirectly impacted by mining. There might not be complete deforestation, but there might be infrastructure, there might be an impact from pollution, that kind of thing. So potentially these emissions are significant, and we'll make this picture here, which is showing just some examples, it's a couple of years out of date, of the greenhouse gas emissions of major mining companies might make these emissions increase once they start to include those emissions from deforestation. So hopefully that gives you some good background and context for what I'm going to go into now, which is to go through a case study for what we think these emissions are at nickel mine sites globally. The first thing I want to say, I'm in a friendly audience for this, but we can't just stop mining. I think here we mostly know that. I'll go through the numbers for nickel to explain why, even if we increase recycling as much as we can to 100%, we still are going to need a lot more nickel for the low carbon technology, for the decarbonization that we really do require to mitigate climate change. So there's different places where you can look for projections of what we're going to need going forward into the future under different climate scenarios. One data source that I really like is the International Energy Agency Critical Minerals Outlook reports. So I took the one from 2024. And there's two diagrams here. And they show two different climate scenarios. So the first is the announced pledges scenario. So that's what countries and companies have announced today, what will be required to achieve that. And the second one is net zero emissions by 2050. So that's the difference between the two scenarios. On the one diagram, the demand outlook, you can see that today there's demand of just over 3 million tons of nickel per year. And until today, although use in batteries and other low carbon technologies is rapidly increasing, still the majority of nickel is used in other uses, and that's mostly going into stainless steel. That demand, those other demands are not going to go away. They'll increase a little bit depending on what happens with global development. And then in addition to that, you're going to have a big ramp up of demand in the green for nickel for use in low carbon technologies. And so the situation that we're going to be in by about 2040 is that we're going to need to produce over 6 million tons of nickel. So we're going to need to double global nickel supply. And you won't be able to do that without opening new mines, expanding mines. So we are absolutely going to have more land use change to produce nickel. And you can see in the other diagram, the mining requirements in the green. This is the expected supply from announced projects. And then under the two scenarios, how much additional supply we're going to have to come up with from new projects in order to supply the nickel that we need for this low carbon technology. If we look now briefly at historical nickel production, one thing that's interesting about nickel, some of you may know this already, but for those of you who don't, I want to talk a little bit about the two main deposit types that we have for nickel, because it's relevant when we start thinking about deforestation and land use change. So nickel, if you go back to historic production all the way back into the 1800s, it's mostly coming from two deposit types, a sulfide deposit and a laterite deposit. And I'll explain what those are on the next slide. One thing that you'll notice in recent years is after a lot of initial laterite nickel production in the 1800s, which was mostly driven by New Caledonia, where you have a lot of nickel mining, you then had a big dominance of sulfides, which is primarily driven by the deposits in Russia like Norilsk and by Sudbury in Canada. What's starting to happen over the last couple of decades is that laterite production is increasingly becoming important. This graph goes up until 2021, but just as an example, for last year, more than 50% of global nickel production was coming from laterite deposits in Indonesia. So laterites are becoming more and more important going forward. What is a sulfide versus a laterite nickel deposit? Well, sulfides are found, the full name you could say is magmatic sulfide. They're found in igneous rocks. I'm not going to go into the detailed classification of that. I think many people could give a whole hour or two lecture on that, but I'll just briefly say that they're found in igneous rocks. So for example, in magmas, or they can also be found in lava flows, komatiite deposits. And they tend to be concentrated in those igneous rocks, defined footprints, generally higher grade. And so generally you could think, but we'll see in a minute, this may not be true. You could imagine mining that with a lower footprint. A lot of those sulfides can be opened as underground mines, which of course have a lower footprint. And that's because of the way that the deposit formed in that igneous rock. Laterites, on the other hand, are interesting. They're found in soils. So you have igneous rocks underneath, generally ultramafic rocks, but generally those rocks don't have high enough nickel grades to mine directly. But when you have intense weathering in tropical environments, you get that nickel moving into the soil, into that weathered soil, and upgrading so that you can mine that soil, basically strip mine that soil. You cannot develop a laterite mine as an underground mine. It has to be an open pit mine. So when I first started this research, and I was thinking about this footprint and potential differences with commodities about where you produce them, I thought nickel would be a really interesting example to look at, because my theory going into it was that probably the footprint and the deforestation from sulfide mines is potentially a lot lower than the footprint and deforestation and associated carbon emissions at laterites, because laterites tend to form in tropical environments, they're big open pit mines, so on and so forth. What you'll see in reality when you get to the data is that that's too simplistic. You may generally be able to say that for certain deposits, but there are a lot of sulfides that also have big footprints. But I thought it was interesting to think about that because you have these two very different deposit types that can be found in different environments for nickel. So here I have a slide with too many words on it, where I've tried to summarize in one slide what we did over a couple of years. So I'll go through these methods relatively quickly so that I can get to the results in the interest of time. But if anybody would like to go back at the end or talk to me afterwards, I'm happy to explain in more detail exactly what we did. And you can also read our methods in the Nature Communications paper that was recently published. So before we could get a sense of global emissions and global variability in emissions from deforestation at mine sites, we had to figure out where these nickel mine sites are. And that's not as easy to do as you think. There isn't always a great global database for mineral deposits. And we wanted to look not just at existing historical mines, we also wanted to get a view of where future mines might be developed. So where there might be deposits that would be coming online in the coming decades to understand what that footprint could be going forward. So where we ended up landing in terms of a good database is we started with the S&P Global Market Intelligence Metals and Mining database, which isn't perfect, but it's really good. There's a lot of information there. And then what I did as well is I teamed up with Gavin Mudd, who used to be here in Australia. He's now moved to the British Geological Survey, and he has a huge database of nickel mines and production. So what we did is we actually ended up combining the two sources of information. And where we landed was a really excellent compilation of nickel mines and deposits, where there were 481 deposits. And we drew the line at deposits that had reserves and resources. So there was a drill hole, somebody had produced some kind of report. It might not be perfectly code compliant, but at least we knew nickel was there rather than, say, exploration targets that just have geophysical data or sort of lower down the exploration ladder, so to speak. Once we found out where all those nickel deposits were, a lot of them had really poor quality data. So in the S&P database, for example, 245 deposits had no geological classification. So initially, we didn't even know if they were a laterite or a sulfide. So what I did, and it took a while, is I went through all 481 deposits and I manually classified them with other information, company websites, geological reports, comments in the S&P database. And I fixed up that S&P database. And actually, some of the classifications in there were wrong. So I fixed it to make sure that it was accurate. And then where available, I compiled the production data. And that was a real limitation as well. We were not able to get cumulative total production data for every historical nickel mine. It was actually really challenging to get good data for that. So in the end, we ended up with something that I think is statistically good, but we would have loved to have more. We had cumulative production data for 18 magmatic sulfide mines, 18 laterite mines, and then we also had sort of aggregate cumulative production data for the major mining fields of New Caledonia and Sudbury, and we could map out those footprints. For the mine sites, the mines that have been developed, for those ones where we were able to get cumulative production data, what we then did is we used satellite data to map out the footprints. I worked with Tim Werner in Melbourne on this, who's a real expert in satellite mapping. And we mapped out the footprint of those mines as accurately as we could. And then what we did is that land's already disturbed, so we don't know what carbon was lost. But as a proxy, as a way to estimate it, we played around with buffering around those mine sites and determining what the carbon was around them. Now, we might actually be underestimating it because for old mines, there's probably been a lot of disturbance around the mine, but at least we're getting some idea of what carbon was potentially lost within that mining footprint. So we used that and we played around with a lot of statistics to figure out the best way to do that. And then we estimated what had been lost by just doing a simple calculation, just multiplying one by the other. For the undeveloped deposits, it was a little bit easier, but also a little bit more complicated. What we did is we just took the coordinate and we drew circles around it, and we looked at what biomass is there. So that actually would be what really could potentially be lost in the future. What we don't know for the undeveloped deposits is what their footprint potentially is going to be. And it may not be the same as historical mine footprints because a lot of the deposits that haven't been developed, maybe they have a lower grade. There's a reason they're not developed yet. So rather than picking one footprint, one size for the mine, or one size for sulfide and one size for laterite, the way that we decided to tackle it is we did a sensitivity approach where we looked at a range of potential footprints, and then we would demonstrate what the impact would be depending on how much land was disturbed at each of those sites. So that's what we did. In the end, I think it was great. We ended up with some really good outputs. We had really good data, first of all. You know, the calculations that we got to, the carbon calculations, they're not hard. It's just multiplying one thing by another, dividing one thing by another. But what's hard is getting the data to be of good quality so that those numbers that come out the other end are good. So we had a good, accurate database of nickel deposits and classification, their location, sizes, types, so on and so forth. And then we calculated something that I'll explain in a minute called the land transformation factor, which is a factor that is important. It's used in things like life cycle assessment databases to assess different environmental impacts. And then we managed to get at least an estimate, an idea of what the range of carbon emissions would be from deforestation at these sites. So let's go through that data. So first of all, here's a map where I've plotted this database of these 481 deposits, and I've put them on top of that above ground carbon biomass map of Spahn et al. That shows that global distribution. So you can see the scale for that going from 0 to 100 for above ground carbon. These sulfides are in purple, the laterites are in the turquoise color, and the deposit size is indicated by the size of the circle. What I've also done, just to give you a sense of what this footprint mapping looked like for these mine sites, is there's some insets. So we have 2 laterite mines, for example. So we've got Ambatovi in Madagascar in a tropical environment with its footprints. And then you've got Murrin here in Australia, which is a laterite, but it's a paleolaterite, so it's in the desert. So even though it's a laterite, there isn't actually deforestation in a significant way associated with it. So not a lot of carbon emissions there. And then a couple other examples of sulfide mines. So you've got Kivitsa and North Talnak in Russia there. Again, just showing what some of the sizes are in terms of the mine footprints. So we mapped those for all the mines that we could. When you think about land disturbance, it's not really fair to compare the land disturbance of one mine to another directly, because some mines produce a whole lot more nickel than others. So what you actually want to do is look at the ratio. You want to look at the total land disturbance divided by the total production. That's a way that you can kind of, in a more fair way, compare between one mine and another. So this is just a map, just showing cumulative nickel production versus total land disturbance. And you can see some of those big producers, so New Caledonia and Sudbury and also Norilsk, just producing lots and lots and lots of nickel compared to the other mines. But of course, the other mining operations are also important contributors to nickel production. And taking this data, what we can do is we can produce something called a land transformation factor. And again, what this is this is a factor where you're looking at the land disturbance, and we're looking at it here in units of square meters over tons of nickel production. And a really key outcome of the study is that we produced this table for all of these sulfide and laterite mines. And you can see there, it's a little bit small, but you can see the land transformation factor. And before I go into what those land transformation factors are, and you can see if you start looking at that table that they're highly variable, the land disturbance versus the ton of nickel that's produced. And there's many reasons for that. But I wanted to look at, well, what do people use now? Because land disturbance factors are used in life cycle assessment. They're used in reports that scientists write about the environmental impacts of mining. So what is already existing in the literature? So there were a couple of sources of information that were most commonly used in academic papers, for example. So one is several years ago, the Nickel Institute wrote a report, and they came up with 2 values for 2 different types of nickel mines. So their value was 0.76 square meters per ton for underground mines and 1.8 square meters per ton for open pit mines. The EcoInvent database, there's a very well-known 2009 report about metals that has a value of 1.7 meters square per ton of nickel. That's for open pit. They assume the land transformation factor for an underground mine is 0, is negligible. That gets widely sorted in academic papers, cited in academic papers because it's acceptable. If you go into the EcoInvent database now, I'm not an expert in this, but I talked to a colleague who knows about LCA. Depending on what variables you select, for nickel mining, you do get land transformation factors that can go up to about 10 to 20 square meters per ton. But what is the reality? So that's what we've determined now in our study. For sulfides, you can see that the land transformation factor ranges from 4 to almost 400 square meters per ton, with a median of about 30. For laterites, it ranges from 7 to 229. So there's a big range, and certainly on the whole, these land transformation factors are much larger than what has historically been cited in literature and used in life cycle assessment databases. So before we even get to carbon calculations, this is a really important outcome. And these land transformation factors are probably not just wrong for nickel, they're probably wrong for a number of different commodities. And I don't think that's malicious. I think that's due to a lack of data. It's really hard to get good data to calculate this. And they're also variable. So really, we shouldn't be using generic factors for this. We should be looking at each mine on a case-by-case basis, thinking about its footprint in terms of the mine setup, the grade, the location. There are many, many different factors that go into this and a lot of variability. We can take these land transformation factors now and the footprints, and we can actually calculate the total biomass carbon losses at mine sites to see if these are significant. So what I found in the study is that for sulfides, and these numbers, they're estimates. The numbers can vary a bit depending on how you do your statistics, on the assumptions that you make. So think of these as order of magnitude. Don't think of these as absolutely correct for the mine sites. Going forward, we really need to get better data. I just wanted to get a good global view of what this is. And what we found is for sulfides, they range from 0.02 to over 10 tons of CO2 per ton of nickel production. And for laterites, it ranges from 0.04 to almost 6 tons of CO2 per nickel. So sulfides are not always better in terms of emissions from land use change than laterites, is one take-home message from this. It really depends on the mine site. How significant is that? It's hard to get good recent data on emissions from nickel mines, so I took some data that's a little bit old. If anyone here has better data, please talk to me afterwards. I'd love to see it. But some studies coming from 2010, 2011 indicated that for sulfide mines, you generally have carbon emissions of about 0.9 to 10 tons of CO2 per ton of nickel. And for laterites, it's more, processing of laterites is more energy intensive. It's about 25 to 45. Now, how significant are the biomass losses from land use change? Well, at some mine sites, the ones that are 0.0 something, maybe they're not so important. You probably should still account for them, but it's not going to dramatically change your greenhouse gas reporting that you need to report on every year. But for some mines, the ones that are closer to 10 or 6, this is very significant. And these can be similar in significance to the emissions that you have from your normal mining production. So I think this demonstrates that at least for nickel, we absolutely should have mining companies reporting on this. And potentially, this is an opportunity for some mining companies to really distinguish themselves in an environmental way compared to some of their competitors. What about undeveloped deposits? I'll take just a few minutes to talk about these. So we looked at these hundreds of undeveloped deposits. I didn't look at it in a very sophisticated way where I tried to say this one is more likely to come online than the other. I just wanted to look at the option space in terms of carbon. And what we have here is, in the top, we have the average above ground and below ground biomass just for all these deposits. And you can see overall, laterites do tend to be located in areas of the world where you've got higher biomass densities. You've got more tropical forests, for example. But there are certainly plenty of laterites that are located in areas with high biomass densities. And then if we break it down by country, you can see that, as we would expect from that global biomass map that I showed earlier, there's not an equal distribution among different countries. And in particular, what I'd like to point out is that Indonesia and Papua New Guinea, compared to other locations, have really high above ground biomass values. And that means that any deforestation, any land use change that you have associated with that is going to lead to higher emissions per ton of nickel produced. Now, what is the footprint of a future nickel mine going to be? Well, you saw that huge variability that we had in terms of land transformation factors. We could probably think about it more and model it more, but it's really hard to know what it's going to be in reality. So the approach that we decided to take in the paper is, okay, let's actually just see what the carbon impact is going to be for a range of land transformation factors. So we went from 0 up to 200, which I thought was reasonable. We had some numbers going up to 400. So that's a plausible range of land transformation factors that you might have for an undeveloped nickel mine. And you can see each line there, that's an individual mine just based on the biomass density that was calculated for that point. And that is, as the assumed land transformation factor increases, you'll see that increase in the tons of CO2 per ton of nickel produced. Now, The problem with the historic land transformation values that are used in things like the existing life cycle assessment databases, and I've plotted some lines for reference here, is that if you use the Nickel Institute values, for example, they're so low that biomass variability doesn't really make any difference. If you use that land transformation factor, you can develop in the most dense jungle, and you're not going to have a significant carbon emission result. But if you use actual land transformation factors, so just as an example, I put Kavitsa on there, you do start to see carbon emissions from deforestation that are significant. And you can say the same thing for the laterite deposits as well. That was the case study for nickel. I wish that I had data to show you for many other commodities. Maybe that's something that we'll have in the coming years. The best that I can do today, I don't have concrete data. The best I can do today is point out this excellent map in a Chatham House report that was produced a few years ago called Mining's Impacts on Forests. And what this map is showing is for a range of different commodities. These are large-scale mines that are located in forest areas. So all I can say today is that all of these mines on this map probably have significant carbon emissions from deforestation depending on their footprints, and certainly should be tracking and reporting these emissions. Figuring out what these emissions are on a global scale, it was tough to do for nickel, mostly because of the data. The calculations, as I said, are simple. I suspect for other commodities, for example, if you were to take something like copper, it would be challenging to do. And one reason that's challenging is that there's a lack of good data, particularly the cumulative production data. So as an example of this, there's a recent paper by Mouse and my colleague, Tim Werner, who is a co-author on this study, that looked at the S&P database, and they determined that 56% of global mining areas that are visible in satellite data don't have any production data in the S&P database, let alone cumulative production data. They don't even have a single year of production data. So it'll be really hard to do this calculation in a good way for many commodity types. And also, I mentioned this previously, but there's a recent study that's just demonstrating this. Land transformation factors for other types of mining, in this case, there's an example for copper mines in Chile, probably underestimated and probably a lot more variable than people have realized to date. So we need to do this for other commodities, but it will be tricky because of the data and because of the lack of awareness and knowledge of this. So let's come back now to these research questions that I had at the beginning. First of all, how significant are carbon emissions from deforestation at mine sites? Well, at least at some nickel mines, they are as significant as other Scope 1 and 2 emissions. So this is something that we should be tracking and reporting in the mining industry. If you're lucky on your site, it's not significant, that's great, but you still need to track and report it. We don't have good information, as I just explained, for other commodities, but I would say these emissions are likely significant at many mine sites around the globe. The second question is, how variable are these emissions? They're highly variable, at least for nickel mining, and I imagine they're highly variable for other types of commodities as well. It's going to be influenced by many factors: biome, mine footprint, ore grade, mining method. One extra thing that I wanted to mention today is there's a danger for carbon and probably for all environmental impacts to open mines that are never going to be economically successful. So some of the worst land transformation factors that I found were for nickel mines that opened, only operated for 2 or 3 years, went into care and maintenance or closed. They never actually produced that much nickel, but the land disturbance was already there. So we need to think carefully about, I think, particularly junior mining companies and development. And the best thing we can do is to keep existing mines operating well and maybe to increase the footprint around those where you can optimize things. And then if you're going to develop new mines, develop them in areas that have a low carbon biomass, but also make sure that the mine that you're bringing into production is going to be a mine that survives, that's going to produce nickel for a long time. Otherwise, the environmental impact per ton of production is always going to remain high. And then who's responsible for tracking these emissions? Currently, they're generally not reported by mining companies. These emissions are mostly included in countries that do this in country-level deforestation reporting. So nobody really has taken responsibility for them. In the near future, mining companies need to track and report these emissions. It's not just me saying this, there's also recommendations from the World Bank and Chatham House, and of course, this new greenhouse gas protocol document that's coming into effect later this year. So what should mining companies do about this? This is my last slide. First of all, land use changes, I've said this several times, they absolutely should be included in carbon accounting. And if you want to remain compliant with Greenhouse Gas Protocol, you've got to track and report these emissions. Doing this is not rocket science. I'm a geologist, and my dad always likes to say to me, it's not rocket science, it's just rock science. In this case, it's not rocket science, it's just forest science. So you need to collect some basic data. You need to know for biomass carbon emissions, for example, the exact boundaries of where vegetation has been cleared. That's survey. That's something we do on mine sites all the time. You need to know the biomass densities of that clear vegetation. And ideally, that should be through a combination of satellite data and on-the-ground field surveys, measuring the widths of trees and that kind of thing. And then you should also, it's to your advantage to track any recovery of that biomass in the same way, the boundaries and the exact density of carbon that's recovered. You can't just get away with accounting for this, say for next year, for 2026. The accounting for this type of emission, you generally look at kind of averages over 20 years. So you need to be in a position where you're actually getting data retroactively if your operation has been in operation for a while. And you need to think about this data over long time periods, not just a single year. Ideally, you should use what the IPCC refers to as tier 3 level data collection. So not just a global satellite estimate, but actually on the ground data. There is a place for satellite measurement, but you need to get in the field and you need to measure this on the ground. That's the most accurate way to do it. If you can't do that, for example, for historic land disturbance, you can go to other approaches such as modeling approaches, use of satellite records where they exist, so on and so forth. And then the last recommendation that I would have for mining companies is that you should prioritize mine development in areas that have low biomass densities. And if possible, you should completely avoid areas that have irrecoverable carbon. Thank you. I'll be happy to take any questions.
Thank you, Evelyn. We've got some time for questions.
Thanks, Evelyn, for a nice presentation. During my PhD, I work a lot of ultramafic rocks, including New Caledonia. And you see, if you're looking at the ultramafic terrain, you have a lot of serpentine. It's a mineral. And you show like those areas, you lost a lot of carbon through deforestation. And there is a lot of work doing that. They show that serpentine could be a good carbon storage material for those type of environments. So would this be a viable option to account for the deforestation?
To offset it through carbonation? That's interesting. So actually my PhD was looking at mineral carbonation. I've worked a lot in that space as well. I think you still need to think about the forest and restoring the forest. I mean, beyond carbon, there's the ecosystem to consider. And where you have high biomass densities, you also tend to have high biodiversity. In terms of that, what I'll say as well is mineral carbonation is really exciting. There is a lot of exciting potential to use serpentine and other minerals for this. Currently, it's not at a high technology readiness level. So it's not something that you can switch on today and use. It's something that's still in research and development. It's still developing, and it's still expensive. So you could do that, but I think before you would make a decision to do that, I think it's important that in the techno-economic models that mining companies put together, they need to value this, they need to track this, and they need to figure this out. And I suspect that if you did a robust techno-economic model for that, you would see that it's probably less expensive to minimize and avoid deforestation as much as you possibly can and restore that ecosystem as much as you possibly can, as opposed to a technological solution which is not ready yet and is still expensive.
Thank you very much, Evelyn. Just a question on your last slide, you had recommendations of ideally what would be required for consistent and meaningful reporting. What is the progress to have this written into the guidelines and or regulations to make sure that it's part of the expectations for reporting, as opposed to, recommendations here?
So I tried to simplify sort of practically what mining companies would need to do if they're not yet familiar with the Greenhouse Gas Protocol land guidance documents. There's actually 2 documents associated with that new guidance, and they're very detailed and they have very clear explanations about how you should exactly do this reporting. And it's reporting that is done in some industries. So in agriculture and forestry, they do this reporting often. So I don't think it would be too different for mining. I think you could essentially use that existing protocol. The IPCC has some guidelines for how to do this as well. What I don't have a good awareness of, and I'd love to talk to some people in the mining industry, is I don't know how aware mining companies are of this and how prepared they are with the data to actually meet this reporting expectation going forward. I don't know if they have a high level of literacy on this or not. Maybe some of them are already aware of this, I don't know. My perception is that generally mining companies are not highly aware of this requirement.
Thanks, Evelyn. First thing, great talk. Really interesting to see that the sulfide mine impacts are really quite equivalent to the laterite. That surprised me, actually.
Depends on the location.
Yeah, obviously, but globally,
It
it's
can be, yeah.
quite significant. I was actually surprised as well to see how low your estimates of Sudbury impacts, or I think carbon emissions are. I think it was shown on several graphs, which raises a question of, did you take into account the historical biomass? So Sudbury was massively deforested in the 1880s, and then it's had, you know, from smelting activities, significant sulfur dioxide emissions have impacted the environment. So the biomass there of the modern day is not representative of actually the biomass that mining has removed. And is that error? Well, is that something you accounted for, and is that also something that you did elsewhere?
Yeah, I didn't go into detail about this. We discussed this a bit in the paper. I think the estimates we have there for many mine sites are clearly underestimates, particularly for some of these old historic mine sites. Around the sulfides, you see this in Russia as well. Before there was better regulation, in some places there still isn't good regulation about that pollution from the sulfides. You just had dead forests. And they have recovered to an extent, but no doubt the kind of buffering approach that we did is probably over a forest that is recovering from that and is not the forest that was there before they started mining. So in that sense, the numbers we have here are underestimates. We have to use the data we have. This is why it's really important for mining companies to track this going forward. You could deepen this research. Here we were just interested in getting a rough idea of the numbers and a broad global view, but you could dig in deeper for mine sites and try and improve the accuracy of this, and also try and better take into account these indirect impacts that you have that aren't directly on those mining footprint areas that we mapped out. So probably for many mine sites, these emissions are actually higher.
Thanks. So there is a few questions online, so I'll read one here from Gordon Southam. So have you thought about acid mine drainage, treatment of acid mine drained with carbonate slurries that produce direct CO2 emissions? I'm also thinking of the massive amount of tailings and acid mine drainage that we produced from increasingly low-grade mines.
So I presume that he's asking about that question in terms of forest disturbance. So we didn't look particularly closely at, again, those broader impacts beyond the immediate mine footprint of how mine drainage might impact biomass. So if you did that as well, you would probably find these numbers going up if that's the question that Gordon has, thinking about deforestation emissions. That's a good point.
At the exploration phase in Queensland, certainly any land clearing that's done needs to be offset by purchasing, by negotiating with a local landholder and replanting, revegetating, and that's sort of tracked through regional ecosystem mapping that the government produces. Do you think a system like that? Do you think systems like that are effective long term for offsetting carbon for land clearing in mining? And do you think those sort of systems could then just be moved straight across for carbon accounting as well as just ecosystem management, which is currently what they're employed for?
I think it wouldn't be too difficult to take the data that are collected for those and to determine the carbon impact. I did mention that when you replant something, you sometimes don't recover the carbon that was there. And I didn't look at soil carbon. So if you add that, that's another consideration as well. Certainly, it's a good idea to think about using some of those existing frameworks where you potentially have that data. You wouldn't need to report carbon as part of that. Is that correct?
No.
Yeah, but you could take that system and apply it to carbon, and that's perhaps not a bad idea.
I guess what I'm getting at is, do you think those systems
are effective and well managed and implemented where they have been, like mining companies paying someone to go and plant a bunch of trees to then offset that carbon. Do you think that generally works?
Yes and no. I mean, there's different systems in different parts of the world. I'm not too familiar with how they do it in Queensland and in that space. But I know, for example, in Brazil, where I work, the federal government has rules that land disturbance in certain biomes you need to offset, not just with one area, but actually more areas, which is maybe taken into account that fact that what you're restoring is not the same as what you've disturbed. So that's certainly a good mechanism. I would say to date, at least in the carbon space, that companies have used this, because they're not accounting for these emissions from deforestation. Maybe in that case, it's a bit different with the ecosystem. When they're using forestry carbon offsets, it's generally being used against their other scope 1 and 2 emissions from electricity production and so on. So it's not a terrible idea. And of course, there's mechanisms and markets for using carbon offsets to help you achieve carbon neutrality. However, if you add on the deforestation emissions for some sites, you're going to need even more of that in order to achieve carbon neutrality.
There's a question here online. Sorry, I would apologize to the online guys.
Hi, Evelyn. Thank you. Very good talk. I was wondering, so maybe this is a little bit too detailed, but so when you were talking about the biomass carbon in the trees, so when you cut down the tree, that's where the forestation, when you calculate the emissions, comes from. But another factor is also the ability for the trees to continuously absorb the carbon, right? And going like in the future as well. So if you do cut down a tree, do you also take into account what would have been in the future absorbed as well? Or is that negligible? Is that not really
So we didn't
needs
take that
to?
into account in this study. I'm trying to think if that's generally done. I'm not an expert in that. What I'll do is I'll look into that and I'll send you an email. I'm not 100% sure. It depends where you are in the world. I'll need to think about how significant that is, but it is a good point. You know, you're cutting down something, and we're doing this all over the world, not just for mining, that is storing carbon, not just today, but is your future carbon stock. And we need to think about that. And I think it's particularly important in those irrecoverable carbon areas to think about that. Generally with the accounting, you don't do that, I don't think, but let me confirm that and I will send you an email.
Hi, Evelyn. I thought that was a really great talk, so thank you so much for that. Certainly learned a few things, so I really enjoyed that. One thing I wanted to ask was just about research impact. I mean, this seems like a very important study, and you know, from what you presented, I definitely agree. But in terms of discussions that you may have had since publication with like the Nickel Institute or any influence on the nickel mark, like I guess what's next?
I haven't been talking to them. I'm a little afraid to talk to them. If they want to talk to me, they're very welcome to contact me. I think a lot of people should be very concerned about this. And what I'm trying to do with my publication in this talk today is to raise awareness. And I also ended with the recommendations because I don't think there's any reason to panic. Collecting this data is straightforward. I think, you know, it's a little hard to be optimistic with geopolitical events at the moment, but the first part of solving a problem is knowing what the problem is. And so I think this is a reality. It's here. There's greenhouse gas protocol reporting. The best thing we can do is face it and follow these recommendations and try and get on board as quickly as possible. And if anybody would like to talk to me about how to do that, they're very welcome to send me an email. I'll be happy to talk to them.
Well, join me to thank Evelyn. There's a lot of questions online that we didn't get to, so at some point we might send them to you.
You're very welcome to
address them.
email.
Thank you. Next week we'd have Professor Courtney Young and his PhD student Mitchell Harvey from Montana Tech. So it would be mostly online, but we'll still host it from the lecture theater. They'll be talking about the history of critical minerals and applications of rare earth minerals in magnets, recycling of magnets. So please join us next week as well. Thank you.